Hello, welcome back everyone. We are going to go back to our series of Explain the Exam, where we go through past exam paper questions and obviously explain how to answer it. So today we're focusing on a concept in Module 8, Inquiry Question 2, which is the structure of the atom. And we're looking through J.J. Thomson's experiment to measure the charge to mass ratio of an electron. In this question here in the 2014 paper 28, it says draw an annotated diagram to show how J.J. Thomson performed the experiment. So what you need to do is obviously draw out the diagram, but not only that, you also need to provide labeling in terms of what's happened there. So let's consider. So he used a cathode ray tube. To be honest, my memory of what a cathode ray tube looks like isn't super great, but we'll soldier on. So we have our cathode ray tube. So I'm going to label that my cathode ray tube. And there were a couple of features in it. So firstly, we know that he had a thermo cathode. So we have our cathode here, so that is going to emit the electrons or emit the cathode rays if you like. One of the things he put in it was a heating coil, so around this he provided a little coil, so it was a heat coil. The idea is if you heat up the piece of metal, that will increase the likelihood of electrons being displaced. And then what he had after that was the anode. Now if you remember with the anode, he made sure the inside of the anode was empty, so it was a nice sort of circular form like that. That's our anode. That's the positive component of the setup. Actually, I think there might have been like a tube down here or something like that. Not quite in memory, but that's what we have. And the next thing we have is try and use as many colors as possible, more so let's make sure it's really clear. Then we have the charged plates. So then we have our electric plates. Okay, and these electric plates provide a electric field, so produces or generates an E field and essentially exerts an E force, electric force, on cathode rays, on the cathode ray, like that. We could say that this side is negative, this side is positive. So that's what we have there. Okay. And then the second part of this setup, besides the electric field, was to also have a magnetic field. So we have our magnetic field. The actual application that they used for this magnetic field was called the Holtzmann Coil. So I'll just call out the magnetic coil. And in this case here, let's just use my right hand palm rule or left hand palm rule to help me out here. Okay, so it's going, so the electric field is going up the page. That means that's going to drag our electrons up the page here. So to balance it out, I want to generate a magnetic field that pushes it down. So our magnetic field is going to go into the page like so. So that and what's happening here is the magnetic force will be equal to the electric force. This allows the velocity of the electron to be found. Okay, so that's what we do here. And then what we can also write is in step 2, or we can write step 1, we want the force from the magnetic field and electric field the same. Step 2, the electric field is turned off, so it's at a 0 point here, and this allows for a nice circular motion of the cathode ray here. So originally what we get is the cathode just going straight through. Okay, and that helps us calculate velocity there. If we turn off the electric field, so E field equals to 0, then we can find the charge to mass ratio. So charge to mass ratio can be found, and the way we work that out, if you recall, is by equating the centripetal force and magnetic force together. Okay, so that kind of shows you an annotated diagram of the setup that was used by J.J. Thomson to calculate the charge to mass ratio of an electron. I guess the only other thing you really say is you can say that this is the fluorescent part, and so yeah, we see fluorescence. Okay, next part of the question, calculation 1 this time. It says an electron is projected at 90 degrees to the magnetic field. So what we know here is the motion is sine 90, which means it's equal to 1 in this case. We have a speed of 1 times 10 to the power of 7 meters per second. This undergoes a uniform circular motion. Calculate the radius of the path. Okay, so what we know is that the centripetal force is equal to the magnetic force. If we write the equations out, this is what we get here. Charge to mass that. We want to calculate the radius, so we want to make that the subject of our equation. So if I substitute the mass of an electron, that's given to me on my data sheet. The velocity of the electron is this value here, divided by our radius, equals to the charge of an electron. In this case, I'll just leave the charge as the number here. I know the electron is negative, but you know, the measurement of radius is scalar, so it doesn't really matter in this case. The value specifically, well, don't forget the square. Substitute the value for velocity there, and then we have the magnetic field strength. So the next thing we need to do is rearrange our equation. Obviously the velocity is going to cancel one of them out, so we only have one left. So we have the mass of the electron, just one there, divided by the charge of the electron, and also the magnetic field strength of our electron, and that will be equal to the radius that we need to calculate. So let me plug that into my calculator. I'll quickly pause the video at this point here. Before I go through that, obviously I forgot to add the velocity component that I had there. So velocity. Now if I put that into my calculator after all of that, hopefully I get an answer that makes some sense. Okay, so the final answer I get here is 0.063184 following meters. If we want to round it off, we can round it off to 3 sig figs here. As you can see, they haven't really given us many sig figs to work with, so let's just round it off to 3 sig figs to just kind of put it nicely like that. Now obviously, ideally, you should go with the smallest number you used in the equation, this being 1, so they might have intended for us to write 0.06 meters, you never know, so there's that. One other thing I might just quickly go back into, this is the trajectory if it was velocity. Maybe I'll also draw the trajectory if we expected the magnetic field to turn off. So this circular motion, we measure the radius, to find charge divided by mass, charge to mass ratio. Obviously with our anodes, we also can say slits in middle to accelerate cathode, and then we know that we have a cathode ray tube, and so that is a low pressure system. If you want to draw in the fact that the cathode and anode are connected by a circuit, you could do that as well. So that kind of explains the setup of J.J. Thomson's experiment, the illustration, and we also went through some basic calculations related to finding the radius of the pathway. So hopefully you found this useful going through this past paper question. If there are particular points about J.J. Thomson's experiment that you're not quite sure of, that you need a refresher, please have a look at the video about J.J. Thomson's experiment. Hopefully you find that useful, and also hopefully you find other future lessons useful with this as well. Now, until the next time we do an exam explained, take care.